Okay.
Thank you, Che Azahar, and then good morning, Salamat Pahi to everybody. Okay, so thank you for joining this session along with me. So here I would like to share to you some of the important or maybe interesting facts about intermetallics compounds, or simply we call IMCs. So though this is mainly in the electronic and semiconductor industries, these IMCs are also applicable in all the industries. Let's say for example oil and gas, or maybe temperature based or thermal based industries also. Okay, so in this occasion, I would like also to thank our university for giving this permission to share this some of the information to you all, including Dr. Ranjit, the person who introduced me to Media Lab. Okay, first we look into what is actually intermetallic compounds. Those who are familiar with the word, and you may have some kind of comparison, the intermetallics and then alloys or compounds, are they same or are they different? So I can just give a basic one. Normally, whenever we mix up two components together, two materials together, then we call compounds. Or whenever we say an alloy, it can be a nickel alloy, copper alloy, magnesium alloy. That means the major element is the one. It could be aluminium, magnesium, copper, nickel, which is added with another components or another part of constituents or materials. So if it is more than 80 percentage, it belongs to one particular major material. With that name, we call it as a alloy. Okay, it could be a magnesium alloy, copper alloy, etc. So this is what we can say an alloy or a compound. And why we have to call this a specific name intermetallics. So the name generally tells most of the time they are metals. Yes, it is true. And when we say the word inter, in between. So let's say, for example, if we are combining or if you are compounding one high strength material, one low strength material, then what we are expecting the new material or maybe the new formation. For example, sometimes when I say general, it may be difficult. I can give a direct example. So you have a nickel. Nickel is considered one of the hard metal which has the melting temperature of 1270 degrees centigrade. On the other hand, I have aluminium. Aluminium is considered relatively a lighter material. I'm saying relatively because there are materials such as magnesium are still lighter. So when I say aluminium is moderately lighter material which has the melting temperature of 660 degrees centigrade. So what I am expecting when I am mixing with my nickel and aluminium, one is 1270, another one only 660. So the resultant material, which I can call nickel aluminium alloy generally, or I can call intermetallic nickel aluminium. The property of this one I am expecting between nickel and aluminium. This is what a normal one, like a mathematics. 1 is 2, another one is 1. So 2 plus 1, 3 divided by 2, then the result will be 1.5. But surprisingly, what happens when the melting temperature of 1270 nickel is merged or is diffused or is mixed with a material which is aluminium, which has the melting temperature of 660 degrees centigrade, the resultant material nickel aluminium, which has the property or which has the temperature of more than 1500. So this is something very interesting, right? Because I have two materials and I want to merge them together or I want to alloy them together. But after I alloy it, the property goes to higher than the highest. So here, the among the two material, nickel and aluminium, one is 1270, another one is only 660. So I may be expecting the new material nickel aluminium something around 1000 degrees centigrade with its temperature or melting temperature. But the resultant will be higher than the highest. That means more than 1270, and the new material with the temperature of 1520 degrees centigrade. This is what a simple example. Oh, so is it normally happen only this way? Not necessarily. So sometimes on the positive end, or maybe on the one end, I can say the material can have a higher temperature than the highest. On the other hand, it can be also lower than the lowest. Okay, we keep the same example, nickel, aluminium. Now this time what I'm going to do, I remove nickel and then I include magnesium. So now it's become magnesium, aluminium. So now as usual, aluminium has the melting temperature of 660 degrees centigrade. Now the magnesium is lower than 300, below 300. Okay. So now this time what happened? When this magnesium aluminium becoming an alloy, which I call intermetallics magnesium aluminium. Now the melting temperature of this alloy MgAl magnesium aluminium is less than 220 degrees centigrade. So there are certain materials or certain combination or certain alloy which may have this unique property, and this group of materials are called intermetallics. I hope this point is clear. So why I don't want to call this intermetallics as simply an alloy or simply a compound. Of course, in a general name, all the intermetallics are alloys. No problem. To call it as an alloy, no problem. But can I call all the alloys are intermetallics? Cannot be. Because alloys are normally only certain property. I think with this introduction, let me go to intermetallic compounds, what it is actually. So this IMC or intermetallic compound is defined as solid phases. So that's the primary condition. The material must be only in solid condition. In other words, all the intermetallics are only solids. Very simple. Containing two or more metallic elements most of the time, 90% or even more than that, both of them or more than all the elements used must be metallic, with the rare exceptional that sometimes carbon can also be used. Fe3C, cementite, can also be considered with certain condition and intermetallics. So with optionally one or more non-metallic elements, but the crystal structure differs from that of the other constituents. So definitely what we are looking at is the two materials that are the three materials that we are looking for, they normally have a different type of crystal structure. And the properties of this intermetallics are they are very hot, also they are very brittle, and the major one is especially on the mechanical property or why the industries prefer this particular material to be used is mainly due to good high temperature mechanical properties. This small video, okay, can give us an idea that how the combination works, because normally you may have a many materials characteristics. Okay, so this is a simple unit cell, and this video will be played without sound, so don't worry. So there is no sound for this video. Okay, so we can see there is a simple unit cell. The unit cell now revolving. Okay, so assuming that this is one element, maybe you can take it as a nickel or you can take it as a magnesium, one single element. So now we are introducing another element into that. Of course, still it is considered as one unit cell. Now we are expanding that unit cell. So the property of that particular unit cell now going into one corner, slowly it will be incorporated to every element or the entire system. Okay, so now it is moving into the entire system. So then we can able to see that the properties are now bonded together. The resultant material which may have the property which is stronger than the individual elements. So this is what we can say, either stronger than the individual elements or lighter than the individual elements. Okay, so this is about some intro. Then, as I said, we will continue comparison between alloys and IMC. This one I already mentioned, just to highlight only the points. So alloys normally referring as a solid solutions or randomly mixture of metals in which the elemental crystal structure of the constituent elements is adopted. So this is what we normally say: nickel alloy, magnesium alloy, copper alloy, iron alloy, titanium alloys, meaning to say, out of though there may be few elements present in that, most of the time the crystal structure is dominated or adopted by the main material. So that's why we call it as a nickel alloy. Means the nickel and nickel alloy will have a similar property of nickel. So this is what we can talk about alloys. But when we come to the intermetallics, which we just now looking into that, which has the crystal structure with specific sites assigned for the atoms of each constituent element. Okay, so here it's not going to dominated by one particular element from the combination. It will be combined it and then it become a new material totally, or new properties. And then those who are not very familiar with the word, what does it mean by stoichiometry? So the word stoichiometry means the exact composition. It's a well defined and fixed structure, because this is where the material properties are changed. Later I can show you with some of our results how a small change in this particular composition or that particular area can able to change the entire system. Okay, and then little bit more, intermetallics are normally formed by a process called dissolution or migration. Migrations we normally know it is moving from one place to another place. Okay, migrants. So these are all normally people when they have some difficulty from Africa, they are entering into Europe every day. It's all we call migration. Same, from one area completely moving into another one, and they just stay there. They are not mixing up. Okay, migration is you are moving from one point to another point, but in the new point you just stay there only. You are not mixing around. Whereas if you say dissolution, so from one point to another point you are moving in, but you mix up completely with the people over there, with the system over there, with the materials over there. You mix it up and you will not separate it. You cannot be separated anymore. Okay, and then the intermetallic compounds can be few, and most of the time we look at aluminium is playing the major role. So that's why even if you look at in the literature or if you read any magazine etc journals, normally we call intermetallic aluminides. Okay, so why the term aluminides come? Most of the time, again nothing is 100%, so it's not really like a intermetallic aluminides all the time, but aluminium is one of the material nor mixing up or maybe interacting with another materials easily. Okay, so they can able to have a good combination properties or good dissolution properties or good migrant properties. That's why most of the time the aluminium remains as constant, and then the other material, it can be a gold, it can be copper, it can be silver, it can be titanium, it can be iron, it can be anything, any other. So simply what we can see here, there's a simple structure on one side aluminium, on another side, let's say if you take a gold. So now I'm slowly going into electronic industry, and that's why immediately I choose an example of gold. So gold, aluminium, and then when we go into that, we may end up with very complex structure. Okay, so this complex structure itself showing that the property of the new material or the new alloy or the new IMC is no longer going to be the same as either aluminium or gold. It will be something superior than these two. Okay, and here I'm just highlighting that what will happen, increasing aluminium. So what does it mean by increasing aluminium? To start with, normally what we say, 1:1, one aluminium, one gold. So of course here we have to look into atomic weight, not a normal physical weight, atomic weight based on the atomic number. Okay, so gold, aluminium. And by the time we are increasing aluminium 60%, gold only 40%, aluminium 75%, gold only 25%. So by looking into that, also the structures are changing. So by increasing the aluminium content, what we normally can see, the structure become more dominant. Okay, so this is a phase diagram of the various phases focusing on copper and aluminium. Okay, so now I had to tell, so far I started with gold, then now I am showing with copper. Okay, so at this point I need to mention few things. I think most of you are from the industry and you may know this very well. About 30 years ago, or maybe around 95 to 2000 and all, because before that the laptops are just started using it, and before 2000 especially, if your laptop is cannot be used anymore, you no need to throw, simply you no need to discard, because it has at least about 4 gram of gold, 4 gram of gold in today's price is about at least 800 ringgits. Okay, a laptop which is cannot be used anymore, which has the worth of, it's a condemned one, even it has a worth of 800 ringgits, something like that. Why? It's mainly because during those time the wire bonding, or simply for the others, those who are not very familiar with the word wire bonding, it's nothing but soldering. Very simple. Soldering is connecting the wires. But what's the difference between wire bonding and then soldering? Soldering is we can see in the external way, maybe in the macro scale or in a larger scale. But sometimes the materials or the components that we use in the electronic industry as well as semiconducting industry, the size of the chip used to be very small. Most of the time, microns, micrometer, 10 to the power minus 6. Sometimes the today's latest IC, which has only 72 nanometer. 72 nanometer is 72 times 10 to the power of minus 9. Okay, so nano is 10 to the power minus 9. So such a small chip may have hundreds of bondings in it, hundreds of wires to be connected. So in that situation, we need to apply not a normal technology called what we use a soldering. So we have to go, I can say maybe a nano soldering or maybe a micro soldering. So that particular word is actually called wire bonding. Okay, coming back. Previously, when I say the laptop, they used gold as the wire bonding material. Okay, so what is so special about gold? We all know that gold is one of the malleable material. Even with the 1 gram of gold, you can able to extend even to a kilometer length. So when I say about 4 gram of gold normally used in a laptop or in a, because at those time, I'm talking about 30 years ago or 35 years ago, we may not have a smartphone as good as what we have today. So at that time, the highest technology means only laptop. So the smartphones are not readily available as what we have in today's form. We all may have a Nokia phone or maybe Sony Ericsson. Okay, those days the touchpad one. Okay, and in that situation, laptops are used gold as a wire bonding material, and that's why this laptop become very, even after the usage, people may collect yours and then they can use it. But no need to be so happy if you have any old laptop today. Today, what we have is all like copper, copper wire bonding, which is not any of use, any use. So if you have better, you discard. That's it. It cannot be, get back your money, or maybe don't think that it has a gold, etc. This is about 30 years back story. Okay. So now, when the gold prices are keep on increasing, and then the only good thing about the gold is with the minimum material, we can extend it for a very longer length, or maybe a small material is good enough for the connection. And of course, the conductivity of the gold is also good enough. But because of the various factors, this one on the commercial side, whereby the prices are increasing for the gold. Secondly, the temperature effect, because When the temperature means what? When you are using up your laptop for longer time, it may get heated up. You know, previously when you have a laptop, you have to carry a cooling fan, huh? The cooling pad or cooling fan always with you. Even we have a pad, cooling pad. On top of that only, you can place your laptop, something like that. Now, of course, due to the technology, we have all the inbuilt system. We have a heat sink inside. So, to a certain extent, we are adjusting. I'm not saying that we are removing. We are still can able to manage the temperature effect within the system. Okay. So when the wire bonding may takes place, previously they used gold aluminide, which is an intermetallic material, which has an issue of this particular one. When the temperature goes up to certain, then the wire bonding, the soldering is comes out. Okay, there is no permanent electrical connection inside the system. But the difficulty or the challenging part of all these ICs are they may have very small, but within the smaller area there are hundreds of solderings. So it's very difficult. Even though there is only one soldering comes out, we can repair it. Only choice you have to replace it. So once the company reputation or maybe the issue of the chips getting faulty very often, then only they thought, okay, we have to look for a new material. We cannot depend on gold anymore. And also the gold prices are increasing. Then people are started using another material. Okay, which material we can go on? That's where it comes in with the copper wire bonding. And this is what even today in all the electronic and semiconducting industry, we are using as a wire bonding. Okay, so wire bonding is a joining technique to produce discrete electrical contacts. In a very simple way, it's just a normal soldering, but this soldering used to be done at the nano level or at least at the micro level. So the techniques, because it's smaller, it's not that easy. There are few techniques normally using thermocompression, thermosonic, ultrasonic. The word thermo referring temperature. So playing with the temperature, then you can use it. That's called thermocompression and thermosonic. Another one normally is the ultrasonic. Okay, I'm just giving a brief intro. So I'm not going into these details. Okay, so this is what normally happens. The process of wire bonding or the process of thermosonic bonding is one of the important assembly techniques used to make the electronic interconnection from the IC integrated circuit to the external substrate. Yeah, I think another pictures I can show you more clear. Okay, this picture can give you much more better. Okay, so this is what we can talk about. So though it looks like very big, but if you look at the size of it, it's less than 1 micron. So 1 by 1 millionth of what we can see in our normal eyes. Okay, so this is about it, and this is what we can call about how all these, the wires are connected. Okay, so all this wire bonding technology normally takes place. Okay, so this is what we can say using the surface tension, capillary effect, meaning to say you put the material, aluminium material in the melted form. When it comes out, then it will become a, due to surface tension with the capillary effect, it will come as a bond pad. So this is what we call aluminium bond pad. This is the substrate. Normally we call it as a silicon material, and this is the wire bonding technology normally takes place. And this is what how it looks like. So this is all like a wire bonding, and this is the wire bonding circle, how it normally goes into. Okay, so capillary, then forces. So I'm just skipping these procedures. Okay, I can just show you a video how the wire bonding may takes place. I hope you can hear the sound, right, Jazhar?
Yes, we can hear. Yeah.
Okay, thank you. so this is what we can say about how the gold wire bonding, because if you can see there, the needle is too thin, and if we use other material, by the time we are expanding it, at some time it may be broken. The good thing about the gold is it is malleable, that it can be extended to any length. Okay, so now we look at the copper wire bonding, what we are using actually currently in industry today. Okay, so now you may have witnessed the two wire bonding technique both in gold as well as copper. But the major difference that you may notice, when it goes to gold, it is so thin compared to copper. Okay, but the copper wires are still relatively thicker, so we may be using more amount of material. But how much more amount of material? If you notice previously, I said the gold may be used around 4 gram only, but the copper we are using maybe another 18 gram. Today's one, the whole circuit may be used up to 18 gram. So that means there is additional of 14 grams of material is used. But in terms of the price, when you say previously the gold is about 800 ringgits, the 4 gram of gold, the copper 18 gram, it may be only 30 ringgits or 40 ringgits. So these are all one of the reason also how come the electronic industry, or maybe the semiconducting materials or the smartphones and the digital devices, the prices are coming down. It's also one of the main one. So what I'm doing here, okay, after explaining that, but whenever we are moving through the new technology, of course we may have some issues. So with this new one, the copper wire bonding, which I am actually doing some collaboration work with one of the leading semiconducting industry, okay, and we have some issue of the voids formation. So voids, normally we can say a bubble. Please allow me to use another 2 minutes, just I summarize it. Okay, so the voids formation is normally like this. Okay, so I have a copper, I have aluminium. This combination is the one I call it as IMCs. But when this combination may takes place, there is a bubbles coming in due to the temperature one. Then we are studying to either remove it or how much if that property is get affected. So this is what actually I am doing actual the core research into that. Okay, so that one may be a bit difficult for you to understand because the interior one at the nano level. So just to summarize what I have discussed today, so I introduce a new material, or maybe not I introduce, so we come to know a material which is an alloy in a very simple manner, or I can say it is also another compound, but this has a specific or unique property whereby certain combination of materials, when they merge together, the resultant material property will be inferior, okay, better than the among the two materials. And those materials are called intermetallics, and these intermetallics are mainly used in electronic and semiconductor industries, especially in the wire bonding technique. What is wire bonding? Is simply a soldering in a very smaller scale, nanoscale and micro scale, whereby previously another intermetallics gold aluminide was used, and that one, due to the cost as well as some effect on the temperature, now we replace to copper aluminium, and the research is still going on. And this ends my presentation today. And this, I would like to acknowledge my PhD and master students, and also I would like to thank my colleagues, collaborators and others who are either directly or indirectly involving in this particular project. And also I would like to thank Medialab Academy for giving me a chance to share some of our research work in terms of its academic point of view to the participants here. Thank you very much. And that's
Thank
ends.
you.
And due to our thing, maybe my question and answer session will follow after the second presentation. Thank you.
Okay, thanks, Prof. Anand, for the great speech and also presentations. So yeah, please keep like what Prof. Anand mentioned. We will have another Q&A session at the end of the talks of the second speaker. So for the second speaker, we will have TS1 Mohammad Zalman Muhammad Aris. So Zalman currently leads the solution architect team at Enterprise Business Unit in Celcom Axiata Berhad, and he started his career as a test engineer at Intel Technology in Penang, with early involvement in several new product introductions. Then he moved to Lucan Technologies at the height of GSM 2G network deployment in Malaysia and APAC region. Then to Maxis to work with the Maxis time cell merger acquisition exercise. And prior joining Celcom, he managing the IT security transformation project at Shell IT International and AT&T Communication Services. So for today, TS Zalman will present this topic on 5G in safety and security applied in multiple industries. So without further delay, we'll invite TS Zalman to continue with his presentation. On you, TS Zalman.
Thank you, Tia Sasa. Assalamualaikum dan very good morning, everyone. Let me share my slide. Share it again.
Okay, we can see your slide.
I'm sharing one without voice. Okay, can you guys see that?
Okay.
Tia Sasa boleh nampak ya?
Boleh nampak ni.
Okay, all right, right.
Can see your slide.
Okay, Assalamualaikum and very good morning. First of all, thank you, Tia Sasa and Medialab Academy for giving me a chance to share our experience in 5G in relation to safety and security. Okay, but I would like to also acknowledge Prof. Anand just now for his great presentation. That actually brings me back to when I first started at Intel. And Intel is actually an assembly plant for the integrated circuits, and wire bonding is actually one of the major activities there. Okay, so before I start the whole speech, I would like to run a short video of what 5G is all about. And just to refresh our mind, I know 5G is what people have been waiting for, and hopefully by maybe end of the year, we'll probably get to enjoy 5G and all the offerings that 5G can give us. So without ado, I'll just run a quick video, about 2 minutes here.
2G, 3G, 4G. They've all revolutionized the way we live our lives. And Ericsson has been leading the way. So when it comes to 5G, it's easy to think it's just another G. Well, it's not. With 5G, things will be faster, And we mean a lot faster. With global mobile data traffic doubling every 18 months, the world's demand for high-speed connectivity increases every second. And that's where 5G comes in, by efficiently providing the capacity for massive data growth. So what does this mean for you? It means high-speed connections for everyone always. Fast and uninterrupted sharing, streaming, and browsing, so that you'll never have to fight for data, no matter the competition. But it's not only about speed. 5G will reduce latency to a minimum, making delays virtually impossible to proceed. It means elevating reality even further. It means fiber speeds without fiber at home, for everyone everywhere. And with network slicing technology, every connected service can get its own unique part of a 5G network, fully dedicated and guaranteed for each specific purpose. It means the Internet of Things on an industrial scale, making society more sustainable, increasing resource efficiency, connecting vehicles to get there both faster and safer. It means protecting the most vulnerable road users, detecting accidents before they happen, and helping save lives with dedicated networks for critical services. With Ericsson's leading 5G technology paving the way, the full potential of connectivity is becoming reality. Join us. Let's explore 5G.
Right, so that's in a gist of what 5G is all about. At Celcom, we started our 5G journey in 2017 in our lab. Then in 2019, we participated in the MCMC 5G demonstration project in Putrajaya, where we had, among other things, autonomous vehicle, drones, and also hologram. And then we moved on to Langkawi in 2020, in January 2020, where we had several installations of 5G use cases. After Langkawi, we moved to PJ, Sunway, and also in Terengganu. And today, this is where we are today. So from the video just now, some key takeaways I like to highlight. When the speaker said about high speed, so that's basically enhanced mobile broadband or AMBB. And then she spoke about low latency, is ultra high reliability and low latency URLCC feature. And also she spoke about the IoT, which is the massive machine type communication or MMTC. So all these three features creates this triangle. So all the use cases sits within this triangle. Note that voice is already in the middle. So voice is not a feature in 5G. So it's like we can do voice in 2G. In 5G, you can also still do voice. But what's more important are the ones at the top here: gigabits in seconds, self-driving cars, mission critical broadband, sensor networks, and all that. So if you are like me, I cannot remember EMBB, MMTC, and all that. So the way I remember is high speed, low latency, millions of devices. That's 5G for you, right? So if you joined the previous session on session 3, where Associate Professor Dr. Masrul Nizam shared about computer vision in era IR 4.0. So I would like to take that further to say that we can create camera as a sensor in the IoT space. So let's take a look at basic IoT infrastructure or architecture. First thing, we have all the smart things. The smart meter, your robots, your smart car, smart watch, smart home, everything smart there. And then it will actually transfer data via some sort of network, be it wired or wireless, Wi-Fi, Bluetooth, 4G, over to a centralized data warehouse. Let's say usually it's on the cloud. and then we run AI and machine learning on top of it to create applications, dashboarding for us to take actions. Because now you have a lot of data, but without realizing or manifesting into actions, it's meaningless. So my take is, I would remove all that and say camera is also a smart thing, although it's a normal camera that we have now. Now just that the sensor is now ultra high definition 4K. And we transfer data over 5G and using computer vision or machine learning to extract information out of the image. And you get meaningful information, and also you can do descriptive, diagnostic, predictive, and also prescriptive actions later on. What does the bandwidth requirement look like? Now, let's say you have 10 ultra high definition 4K cameras and running at highest compression rate with 15 frames per second. So the bandwidth requirement, network bandwidth requirement to run all 10 cameras is about 90.4 megabit per second. And when you say, Zalman, 19.4, it's quite easy, right? Yeah, mind you, this is uplink requirement. This is not downlink requirement. Okay, so if you flip up your smartphone, you do your speed test right now. Uplink, downlink, you probably get about 20 to 30, depending on where you are. But uplink is much lower than that. So if you put a 4K camera on a 4G network, you will see something what we call teleportation effect. One frame you see one person this side, the next frame you see this person moved to this side without actually seeing them move. Okay. Let's look at some sample use cases we have in safety and security. By all means, this is not an exhaustive list. This is just for us to share, to debate, and discuss how we move forward. All right. First thing first, vehicle analysis. I think Prof. Masruliza mentioned this already in his last talk, where we can have an image of let's say a road, where the computer vision can identify whether this is a car, a bike, a bus, or a truck. Then we can go one next step, which is to create to identify the characteristics of the vehicle, license plate, color, location, speed, or even if this car has a previous violation of speeding ticket, parking ticket, or whatever. Then, if actually the car does, then it can flag. It says, "Oh, this car already has 2 violations before, and now it's illegally parked on this road." Okay. So, how is this information is useful? The PDRM can take this information and start dishing out summons, for example, or sending notification to educate the driver. You cannot park here. You park again, it will be a summon to you. Okay, traffic control at a busy intersection. Okay, when our office was in Jalan Semarak, this is my view from Jalan Tun Razak and Jalan Lampang intersection on a Friday at 6 o'clock after it rains. It's exactly like this. Okay, so and then there will be a couple of traffic policemen will come and help sort all this out. But what if we take all those we install cameras on the traffic lights, we control traffic lights and the cameras using AI. But this is not replacing the traffic police. It's helping them. Because remember, this is still machine learning. The model still needs to learn over time. The knowledge is with the policeman. And also one more thing, when we have policemen and traffic light, the policeman has jurisdiction over traffic light, right? So we have to follow what the policeman says. So if things get out of hand, the policeman can step out and take control of the whole situation, right? And then the process repeats itself, learning and deploying, until it is intelligent enough to deal with different types of scenarios at this junction here. Next, facial recognition and people counter. So now we are in COVID. Every time we go into a premise, we have to scan our face, scan our temperature, log in into My Sejahtera and all that. So all of that can actually be done presumably automatically in the future. But what this does is that to take one step further, says, okay, I see this person coming in. So what can I tell about this person? Can I say this? Can I match this person to the previous sessions that this person came into this premise? And where did this person go to? Example, in a mall. Dia pergi shopping spot sahaja, example. Or dia masuk the other areas, right? So with that, you can actually do two things. Number one is securing that you know that this person is not a threat to your premise, and number two, that is actually a marketing opportunity. So we can take that one step further. Crowd control. Hey, yeah, now we don't have crowds, but inshallah after COVID we can go back to our normal life, pergi pasar malam and all that. But this is an area where the authorities would like to have a bit more control. They want to see in some section how many people are there. In this section, how many people are there? Because number one is whenever there's an emergency and exits are not enough, so there will be stampede and things like that. So there will be cause chaos in this whole area. So whenever we have an event like this, the authorities will want to know where the people congregates and how do we move them in an orderly manner out of this area when there is an emergency. And secondly, is also look at, see if you have, example, wanted people. Do you see them here? So those are the facial recognition applications. After you start recognizing the face, you don't have names associated with the faces, but at least you can recognize, oh, this person went this one place and he also moved to another place another time, right? So you can actually do the tracing. Next one is perimeter monitoring and intruder detection. So this is also another use case for 5G and also cameras. So you can see this person trying to hop over the fence, but this is only for a closed environment. What if you use drone to patrol our country's border? So that is actually a huge application by itself, right? Okay, next one. I'll share this statistics with you. This is from DOSH, Department of Occupational Safety and Health. So in 2020, there were 6,933 reported occupational accidents in Malaysia. And if you look at the highest sector impacted, penghilangan and also pembinaan. So I believe those accidents can be avoided. So because that's why DOSH is here, all the safety rules and stuff needs to be followed. So let's say we have a camera that can do this, detect somebody that is violating the safety compliance. Let's say, for example, not wearing a safety helmet or not wearing a safety vest, or smoking at work where there could be combustion. Those kind of things are instrumental into ensuring that the safety of the work site or your factory is maintained. Okay, so I think that's all for now. That's all for me. I would like to open the floor for discussion. Or Professor, I hand the floor back to you. TSSR.
Okay, thank you, Zalman, for the talk and presentations about 5G. So now we want to open Q&A sessions for both speakers. So floor, maybe you can ask any questions.
I have seen questions in the chat box.
There's one question for you, Prof.
Yes, David. So, is there other cheaper intermetallic component material besides gold, copper used for wire bonding in the semiconductor industry? Okay, so I had to make something clear here. It is not going to be copper plus gold. It is a combination of gold aluminide or copper aluminide. So never the combination is gold plus copper. So that itself is not correct. So I had to clear that first. Okay, because previously we used gold aluminide, AuAl. Currently we are using CuAl. As just now I mentioned that aluminium we still keep it as such because there is no issue on aluminium. So the material focus here is previously gold. As I mentioned that gold become more expensive. Let's say the amount of 4 gram of gold previously used itself costing about 800 ringgit or 750 ringgit as of today. The copper, even though the amount of copper that we are using is slightly higher, but still it may be at least 20 times or 20 times, 25 times more economical. So that itself is the answer for you. Okay, but if we still want to go for something more than this at the moment, because copper is considered to be one of the good conducting material with, I'm not saying a very good property, reasonably or moderately it's good. Okay, so if we want to still find some other material, some revelation need to be comes out suddenly one day, a material which never we thought of, this is a material can be used, and we find it out or maybe found out. That's the only choice. But as of now, consider copper aluminide itself is one of the most economical material in terms of your question. Thank you. Or if you have any further on that, please ask me. Then if I know, I can try to answer on that. As our other speaker, technologist one, Mohammad Zalman, he is also from the electronic industry. I hope I can also always ask him because he may be having more industrial experience. So that's why I had to admit on that. So my industrial experience is zero. I had to tell that zero. So we only visiting them and then talking to them only academically, not spending time in the lab. Maybe visiting one day. Okay, I used to visit the lab, discrete component lab or whatever, just few hours with all the procedures we follow, but not directly on the experience. Okay, thank you very much.
Okay, thanks, Prof, for the answers. So hope this can answer Mr. David questions on gold. Yeah, actually, when talking about gold in the electronics, so I think of keep looking my old phones. Maybe I can extract at least 4 grams from each phone, then sell back. It's like can make some money from that. Okay, to Tia Zalman, there's one question here. Will IMC be feasible in car? Automotive application where it is exposed to high temperature for a long time. Yeah,
I think that's for Prof. Anand.
So, this is for Prof. Anand. That's what your question for you, I think. From
Yeah, sure. I'm reading.
Will IMC be feasible in car automotive application?
Automotive application where it is expected to high temperature for a long time. Actually, IMC way back for my PhD work, which is in nickel aluminide, the main application of that nickel aluminide is thermistor. Thermistor is a material which play with respect to temperature. Actually, at the room temperature, it used to be non-conducting. When the temperature increases, it's become conducting. then the process is vice versa. So that's what the normal usage or application of that particular IMC, that is the intermetallic compound nickel aluminide. Of course, again, when we study on that, nickel aluminide also has few phases. If you look at the phase diagram, it is maybe nickel 3 aluminide, nickel 5 aluminium 3, and then nickel aluminium, that is 50-50, or nickel 4 aluminium 6, something like that. Okay, so to go into that, normally in the manufacturing sector, I can say, not easily anything can be changed. There are so much of research. If you look back the articles in the literature, we can see more than 100 over articles of IMCs can be used in almost all the field, not only in electronic, not only in semiconductor. It can be also used in space technology, and then in the rocket technology, or even in aeroplanes. When you go to automotive, they immediately go with the higher tech. Okay, so aerospace applications, in other words. But the thing is, because sometimes the intermetallics with this high-end material, we can say high-end material due to the cost and then the manufacturing, everything, we don't simply use it in the normal application when there is already good technology. So to answer for your question, in car or automotive application, there are hundreds of applications are there, but it is not in just we can see as an IMC. The IMCs are still used. One time I attended a talk in Infineon Melaka, and then the chief engineer there, they explained there used to be 7,800 to 13,000 components in a high-end smartphone. Maybe I think our other speaker is more better on that. I can just what I heard. So 7,800 components in a very simple smartphone. It may go up to 13,000, whereby the iPhones, etc. They are using 13,000 components in a size of 15 centimeter by 7 centimeter. Then just imagine how much amount of materials that we are using. But in that, they said at least 40% of those materials belongs to electronics and semiconducting related materials. Out of that 13,000 components, 40%. So in that case, this 40% of materials already using the wire bonding technology or any kind of IMC material. So then I can say it's all already there, but since we are using at the very smaller scale or nano scale, so we cannot say that IMC used directly in automotive. But yes, it is already used, but not in the direct form. Okay, so even though when I'm saying today wire bonding used intermetallics, but some other people, they may not know even this. They may think that copper, so they may not use the term IMC. Okay, so to answer that question, it is already used. Okay, but we cannot directly take the application of this IMC is suitable for high temperature application. That's why I'm using this. No, that will be another study. So that one is another topic. I'm also working on that, especially on the car chassis, the outside body. Okay, so if you look at the normal material we are using is stainless steel or iron based, and people may be going with aluminium. For example, the car chassis with respect to Volvo, Audi, BMW, Benz, they are all using the aluminium as a car body. And then if you go to Ferrari, Lamborghini, they are using titanium as the car body, including the aerospace applications. Because the physical strength is very high, whereas they are lightweight material. Okay, on that particular aspect, yes, we can go. If you consider that, the price will still become, 10 times, 15 times more. So it's not really that possible on the normal end or the manufacturing sector. It may be on the specific sector. Thank you.
Thanks, Prof. Anand, for the answer. So maybe the next one questions is from IR Dr. Hafizah to Zalman about the facial recognition. Does it mean our privacy is breached without consent? So any cases about that, maybe Prof,
Okay.
maybe Zalman can answer that. Or...
Okay, thank you, Dr. Hafizah. Okay, when talking about privacy breach with or without consent, there are many ways of looking at this. Number one, when we actually step out of our house, because our house is basically a restricted area from people outside, right? People cannot come in. So when we step out into a public space, you are actually in a public space. So people can see you, people can say hello and whatever else. So when you do facial recognition or even capturing of image, there are always two schools of thoughts. Number one, yes, you are breaching my privacy. But then the other people will say that if you don't want people to breach your privacy, stay home. Don't come out. Right? So that's one argument. The other argument is, yes, they captured your face, but there's no name associated to it. Right? So we can argue also like that. So I know your face, but I do not know who you are. I do not know where you live. I do not know your IC number and all that stuff. But there are in the world, this has been implemented in major cities in the world, especially China and the US, and possibly the UK as well. Right. So, but I think the legislation differs from country to another. So I think if we want to implement this in Malaysia, we have to work up to with our legislators to define how this data that's being captured is, number one, captured, processed, and also stored. I hope that answers Dr. Hafiza's question.
To Zalman, there's one more question from Hu. It's about estimation of the cost. I'm not sure whether Celcom have this package of facial recognition class, or is this solution is commercials, or is maybe you can share about a bit about business strategy of Celcom side on this?
Well, I'm talking about Celcom. I'm just talking about the industry and the products available in the market right now. So as people starts to get more skills to create machine learning algorithms for facial recognition and all that, the prices of the software reduces, because what you want to find is software that can work with any hardware. So I don't want to come with a brand of camera and say you can only use my software to do this. So that's going to tie you down into a single vendor or single provider. So what you want to do is take a camera from just anywhere, be it from a low end to the highest end, and feed that into a software that can still do the facial recognition for you. So, but having said that, yeah, you probably need to have a bit more technical knowledge how to integrate those two together. Right. As for estimated cost, like I said, cost is coming down. Camera cost is also coming down. There are already software out there that is open to integrate with any cameras. So those are also coming down, and you can actually, I think they sell it as a service rather than you buy the whole package. So that basically brings down even further your cost of subscribing to that service. Thank you.
Okay. So there's two more questions. I mean, coming from Floor, Mohammad Al-Hafiz and Abdul Rahim. I think about the same, about 5G infrastructure and also SPV. So,
okay. 5G
do you have any comment on
ready for Malaysia? Okay. So 5G infra. I'm sure you have read the news that the government has announced DNB, Digital National Berhad, as the party to deploy 5G network in Malaysia. And I think from the newspaper clipping that I saw, they promised to deploy in KL, Putrajaya, and Sabada by the end of the year. So I think, and they just awarded Ericsson the contract. Right, this is all published, it's all public domain. So yeah, we will be ready by end of the year. So that's what they're saying. Is it true Thailand is more advanced in 5G network in Southeast Asia? Well, I think at this point in time, countries around Southeast Asia are competing to get 5G into their domain. not just Malaysia, Singapore, Thailand, probably the other countries as well. But I do see some reports on news clippings that Thailand has some network already up. Okay, Cik Abdul Rahim, the new decision of government for SPV rollout. What is the strategy for telco player to implement this kind of rent sharing? At this point in time, I cannot answer this question directly because it's still in the talks. So I really don't know.
So yeah, since we already at 12 o'clock, 10 minutes more than expected. So I think we'd like to thanks to all speakers for the knowledge sharings, and as a part of learning program for our professionals and technologists, especially in telecommunication and broadcasting technology area, and also in other areas, related areas. So before we end the sessions today, I would like, we can open everybody camera. Maybe we would like to take photo sessions for the last. Dr. Hidayah?
Ya.
Boleh
I'm waiting for
buat sesi bergambar.
Okay, saya tunggu ramai buka kamera dulu. Okay, thank you everyone. Done.
Okay, thanks to everyone, to
Thank you all.
So for the sessions today, and then see you next time. Next month we will have another sessions. First week of September on the first Monday. So keep updated to all. So, thank you. Thanks to the speakers.
Thank you. Assalamualaikum.
Right.
Thank you.